Okay, the recording is started. Now let me what else? Let me check the sound. Now should be fine. Okay, I think I can increase. Okay, so far so good. Okay, so today we talk about connecteds. So it's not I don't think it's a very easy class today. There are some, we are getting into some depths of this theory. So we will talk about connectedness. The property of connectedness is not difficult to understand. So a graph of this shape, for example, so have some part here like this, something like this, and there's no relation, and there are some other bunch of vertices. This kind of graph altogether, this graph is clearly unconnected, disconnected. Okay, so a graph is called connected if you can walk from any vertex to another vertex. So definition, a graph is connected if for any two vertices x and y there exists a path or a walk from x to y. Okay, so it's I think it's easy to understand. So let's start from an easy theorem. So in fact, connectedness has some restrictions on the size of your graph. Theorem. G has, for example, k connected. So okay, so in this case, we call this a connected component. So this is a connected okay. So if the graph is not connected, you can split the graph into different connected components. Suppose G has k connected components. Then, in fact, you can get an estimate of the edge number of G. So the edge number of G is at most half of n minus k times n minus k plus 1. Okay? So what happened? So you can think a little bit why you can actually estimate the size of the edge number of the graph. So if the edge number is too little, if the edge number is too much, then you can guarantee your graph is cannot be k connected. Cannot have a k connected component. In particular, if you have two connected components, your graph has to split into two parts. And if you have too many edges, what happens is that you cannot do this. Okay? So suppose, let's prove this. So if G has k connected components, then you cannot have too many edges. Suppose G has k connected components, the size of the k connected components these k connected components are, for example, A1, A2, A3, and AK. Okay, so suppose your graph can be split into k parts, and here you have a size, vertex number. Here you have A1 vertices, here you have A2 vertices, here you have A3 vertices, and so on. And here you have AK vertices. Okay, if the graph has as many edges as possible, then at most you can make each part a complete graph. Do you understand what I'm saying? Does it make sense?
Não entendi essa última parte.
Sim. So for example, here this part has A2 vertices, and it's not a complete graph. Then you can add more edges such that it becomes a complete graph. And then your graph has more edges in total, right? So in the end, we can make every part a complete graph, but we cannot add an edge between two parts, because otherwise we make it connected. So it violates our assumption that in total all these parts are connected components. All these parts, they are not connected with each other. So in this situation, how many edges do you count? So here you find A1 choose 2 edges, right? Here you found A2 choose 2 edges. So in total, there are AK choose 2 edges, right? And this number is the total number of edges, right? This number can be maximized. When I say maximized, I mean that you change the values of A1, A2 until AK. So far we only know that n, the total number of vertices, it equals the sum of A1 plus A2 plus A3 until AK. So we only know this. So we have the right to change the values of A1, A2 until AK. Okay? So this number can be maximized if almost all of them only have one vertex. So look, A1 equals A2 equals until AK minus 1. All this equals 1. And AK equals what? Equals n minus 1 plus n minus k plus 1. Okay? So it means that the graph will look like we have one vertex here, no edge. So another vertex here called V1, V2, and V3 until Vk minus 1. And the remaining vertices, there are Ak equals n minus k plus 1 vertices. And here is a complete graph. So in total, the edge number is Ak choose 2, which is n minus k plus 1 choose 2, which equals 1 over 2 n minus k plus 1 times n minus k. Did I write this number? Yeah. Okay? So it is actually n minus k plus 1 choose 2. So this is the maximum number possible of the edge numbers. It is achieved by this graph. So every part has one vertex, except the last part has more vertices, n minus k plus 1 vertices. Okay, this is not very difficult, and I'll leave, so this is the proof. I'll leave as an exercise for you guys to consider the special case of k equals 2. So basically you repeat this argument, but here to actually prove that the number is maximized by this is requires some computations. I will leave this for you as an exercise in the case k equals 2. Okay? Okay, so you understand what's going on, right? It's not very difficult. So in the case k equals 2, it's just you put it in 2 parts, A and B. And you get 2 complete graphs. And then you can compare, you realize that it's the best, you get the best, the maximum number if one part has only one vertex. And if, let me get back to this. So in this case, you have a Ka and a Kb with A plus B equals N. And then you get A choose 2 plus B choose 2. And you prove that this is always smaller or equal than N minus 1 choose 2. Okay? So this is an exercise. Okay, this is really just warm up. So let me continue with the theory. So if a graph contains a special edge, say E, if whose removal will disconnect the graph. Then we call E a cut edge. So I think we more or less, we mentioned this before. It's kind of like this. You have an edge E, which is special. For example, this edge has 2 end vertices U and V. Somehow, here is part of your graph, and here is another part of your graph. And they have no relations with each other. They cannot connect them if you do not go through the edge E. So in other words, G minus E, so delete the edge E, becomes disconnected. In this case, you call this guy cut edge. So this edge E is called a cut edge. Sometimes people call cut edge a bridge, which is kind of vivid, which is nice. It's like a bridge. You go from here to another place. It's like a river split the 2 parts of a city, and you go from here to there only by go through this bridge. So it's called a bridge. So many authors use bridge and others use cut edge. Both are useful. Okay. For example, you can draw some more specific examples. For example, you can draw a cycle here, and maybe some complicated stuff like this. So this guy is a bridge. Okay. A little more trivially, for example, you have a graph like this. This is my graph. V1, V2, V3, and V4. This edge, is it a bridge or not?
How about?
Yes, you still call it a bridge. Okay? Correct, it's a bridge. You call it a bridge. If you remove it, it will create a graph triangle and an isolated vertex. So in our language, an isolated vertex with no edge at all is also a graph. If you accept this, so this is my G, then G minus E will be 2 parts. We have a triangle V1, V2, V4, and an isolated V3. So there is no edge between them because the edge has been deleted. But still, the graph is a disconnected graph with two connected components. Like our example here. So when we make this computation, in the end, I make one part with only one vertex, and here we have a complete graph k n minus 1. Okay, there is no edge between them. So here, this guy is an isolated vertex. So this graph has no edge, but we still treat it as a graph. Sometimes it's convenient, as long as you know what you are talking about. So and it make your notations consistent. So right now we call such a graph still a graph. It's a strange graph with no edge. Okay, so let's see some examples. So let me first example. Let's consider the complete bipartite graph. The complete bipartite graph. Okay, so sorry, I still need some more definitions. So it's a okay. We now know what is a cut edge. So how about when you delete one edge, it's not enough. Okay, so let's give more definitions. A disconnecting edge set. So in the previous definition, one edge is a disconnecting edge set. So here, more generally, we can get a disconnecting edge set in a connected graph. Is this thing is a set of edges whose removal will disconnect the graph. Okay, so this is not so common, because there is another definition which is called edge cut set. Which is a minimal disconnecting set. So what happens here is that probably when you delete some sets enough, then you stop here. You don't delete more edges than necessary. Okay? So finally, we will define the edge connectivity. So there are, like before when we study Euler tours, Euler walks, there are many definitions, but they are related and it's natural, so it's not so difficult to remember. There are some subtle differences, but in the end you can understand. So the connectivity, edge connectivity, which we call lambda of G, is what? Is the size of the minimum smallest, let me say, smallest edge cut set. Of G. So this number exactly is what you think it is. So it means how many edges, the smallest number of edges, when you delete it, you can make the graph disconnected. Okay? So this is called edge connectivity. So And there is another thing, so people will call G K connected if lambda of G is greater or equal than K. Okay? So for example, I have let me consider a cycle. Let me consider a cycle. So here is a cycle. I don't know, 1, 2, 3, 4, 5, C5, C6. Okay? If you delete one edge, it's not enough to make it disconnected. But if you delete two edges, the graph becomes disconnected. So the connectivity, edge connectivity of C6 is 2. And since this lambda of C6 is greater or equal than 1, then we call it 1 connected. It is also 2 connected, but it is not 3 connected. Okay? Sorry. We have to say K edge connected. So because there is a related notion about vertex connectivity. And by definition, C6 is both 1 connected and 2 connected. Because this lambda of C6, it is 2. So it's greater than 1 and is also greater or equal than 2. Okay? Is it clear? So I think it's natural. So how many edges? So it's only one question, but to be very precise, we have many different definitions. You only have this question in mind. How many edges do you have to delete in order to make this graph disconnected? In this graph C cycle, the answer is 2. And this number 2 is your edge connectivity. And then for our convenience, because later sometimes we call a graph, okay, the graph is 1 connected, the graph is 2 connected. As long as the connectivity is greater or equal than that integer, you say it is K connected. Okay, I keep making typos because I really want to say 1 edge connected. So here is 1 edge connected. And both, and 2 edge connected. Okay? So if you are, I think it's not so bad to understand this. I'll give you an exercise later to compare all the definitions: connectivity degree, minimal degree, and edge connectivity. So next notion is so-called connectivity. We have to start with a vertex cut. So a vertex cut is really very similar. It's a minimal set of vertices whose removal make the graph disconnected. Here, in fact, is a little. There is a little thing here. You have to consider a very special case that make the graph. So you remove some vertices, and the remaining graph has only one vertex. Or the remaining graph has only one vertex. So let's try to ignore this. This is used to deal with complete graphs. This is only like one example to deal with. So a vertex cut. So there is for example, you have a complete graph with 4 vertices. You keep deleting vertices. It is always connected. So if you start with, for example, if you start with K4, so here is my K4. No matter you keep deleting vertex, you delete one vertex, you delete another vertex, and you delete another vertex. You keep deleting vertices, and the graph is never disconnected. But you have to stop at some point. So by definition, when the graph has only one vertex left, you stopped. And in this case, you still call the 3 vertices you deleted a cut, vertex cut. So there are 2 situations, but mostly we are more interested in the first situation. The second situation is really very strange, but it's designed for us to deal with complete graph. And similarly, we will define kappa, kappa of G, and call the vertex connectivity of G, of the graph G. It is, so, is the size of a minimum, a smallest, the size of a smallest vertex cut site of G. So this is the vertex connectivity of G is the minimum number of vertices you can delete to make the whole graph disconnected. Let me give the same example. For example, I have this C6. Okay? So what happens is the kappa of C6 is equals to also. So you can delete this vertex and you can delete this vertex. So after deleting 2 vertices, the graph becomes disconnected. And similarly, when kappa is greater or equal than K, say G is K connected or K vertex connected. So if you don't say anything, edge or vertex, it means vertex. So usually people say, okay, some graph is 3 connected, it usually means that it's 3 vertex connected. But to avoid confusion, you usually put edge or vertex. But these pair of definitions are related to each other. Okay. I think there is an exercise. I might be wrong. You have to do it to make sure. So for any graph, kappa of G is smaller or equal than lambda of G is smaller or equal than the minimal degree of G. So I leave this as an exercise for you. I think the second part is very simple because, for example, minimal degree of G is a vertex. It has this kind of degrees. And then if you delete all of them, you disconnected the graph, right? But lambda of G is a minimum number. So you know that you delete 4 vertices, you can disconnect the if you delete 4 edges, you can disconnect the graph. But lambda of G is the smallest possibility. So the smallest the size of the smallest cut edge cut. So it's possible somewhere you only need to delete 3 edges to make it disconnected. So, but you don't know if you can actually find somewhere this kind of edge cut. But at least you know that this is a smaller or equal than delta of G. Okay? Something similar argument, some argument similar to this can give you the first inequality. You can try to solve this in your list. Okay? So these are most of the definitions and concepts in this class, and then we will see some examples and proof theorems. Okay, you understand what's going on? All right, so let's continue. So let's see some examples. Now we are ready to see some examples. So first of all, the complete bipartite graph, K M N. The complete bipartite graph. I would like to ask you, what is the connectivity of it? So what is the question is, what is kappa of KNM? So the claim is the solution of this question. The vertex connectivity of a complete bipartite graph with parts of size n and m equals the minimum number of n and m. Okay, but you have to prove this. So for example, n is smaller. Say n is smaller or equal than n. So I want to prove that the kappa of this complete bipartite graph K and M is equal to n. N is smaller than m. I want to prove this. So, for example, if this is my bipartite graph, complete bipartite graph, and here you have n vertices. If I delete all these n vertices, the graph becomes disconnected. Okay? And I want to prove that, so this is the first, this is actually the first direction. So firstly, so for example, this is size A, part A and part B. Part A has size n and part B has size m. So firstly, if we delete A, then the graph become disconnected. So in order to prove that kappa of this graph equals n, what else should we do? We still need to show that no cut edge has size smaller than n. Okay? So for example, we need to prove no cut vertex cut set has size smaller than n. So on one hand, we find a cut set with the size exactly equal to n, and on the other hand, we show that no other cut set has size smaller than n. We have to do both to in order to prove this. So for this, we observe that any if a set, so let me track this fact, which is not very difficult. So if a set does not cover each part, does not cover A, does not cover B, does not cover either part. For example, a set S, it covers some part of the left and some part of B, then it is not a cut set. Okay, the remaining part, they have to connect each other. So the conclusion that you take any cut vertex, vertex cut set, then this vertex cut set, it must contain either all of A or all of B, and the smaller one is A. So it's more efficient if it covers A, and this proves that it must have size at least n. Okay, so this fact implies that any cut set has size at least n. Okay? Okay, is it clear?
Yes.
I think you have. I think you should take some time to think about this. What happens here is that you cannot only do one direction. You cannot say, okay, I find the cut set. For example, I take the set of all the set A. I take a set A, and clearly, if I delete A, there is no edge. There is no edge at all. So the graph becomes disconnected. This is clear. But this is only part of the proof. It only proves that there exists one cut set with size n. And the hard part of the proof is that you have to show there is no cut set with size n minus 1. And you have to argue why this is true. So on one direction, you find the one cut set with size n. On the other direction, you have to show that all cut set has direction at least n. Both sides together show that n is the number of the smallest cut set. So you have to, when you make a, so I think when you start to learn advanced mathematics, the difference with your high school mathematics is the following. You in high school mathematics, you are always looking for an answer. You find the solution, okay, 6. Okay, I got it right. I make the correct computation. But when you are learning higher mathematics, the solution is not all of it. You have to convince yourself all the logic is okay. It goes through all the details. And the logic is perfect, and how to understand this in order to continue. Okay, let me do a more complicated example. So another example is n cube. So the bipartite graph is very easy, but now we are talking about the k cube. qk. What is the k cube? It consists all the k strings of 0, 1. So I mean, it's like so for a typical, let's look at the K3, Q3 for example. So it has 8 vertices. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. Okay, and two vertices is a form an edge if only one coordinate differ. So for example, 0 0 0 and 0 0 1, they are connected, and it is also connected to 0 1 0, and it's also connected to 1 0 0. Okay, so its degree, because there are three connected, the degree of this vertex is exactly 3, because we can change this position, change this coordinate, change this coordinate. So every vertex has degree 3. Okay, so if we call this a regular graph, you already did exercise on this. Okay, so let's look at k cube. This is 3 cube. So let's look at k cube, qk. Let's write qk, and the claim that is that the connectivity of qk equals k. Kappa of qk equals k. Okay. So to show this is not very easy. I don't know if I should do everything. Right. Okay, let's try to do everything. So proof. Okay. Again, two directions. First of all, let's consider one vertex. So let's consider dv, any v. In fact, what I want to do is that you know the minimal degree of this graph equals k. And by previous exercise, this is greater or equal than kappa of qk. So we prove that kappa of qk one direction, so it's at most k. Okay. So next we need to show kappa of qk is at least k also. Okay. So what it remains to prove that any vertex cut S has size at least k. So what happens is there is no, like before, there is no vertex cut which has size smaller than k. Or every vertex cut has size at least k. So for this, we have the proof is non-trivial. We need to induct. We induct on qk. The base case is easy to track. So you think about it. Why is it easy? In fact, base case you can consider Q1 and it's pretty easy. Okay, so it's you have two vertices and one edge. So there is one thing about structure of QK. So when you fix the first coordinate, for example, here is the edges is the vertices, or with first coordinate 0, and here is all the vertices with first coordinate 1, and the remaining, for example, here is some other, for example, 0, 0, 0, 0, 0, this vertex, and this vertex is like 1, 0, 0, 0, because here is all the vertices starting with 1. Here is all the vertices starting with 0. Let's say k equals 4 for simplicity. And here, for example, I got a vertex which is 1, 0, 1, 0. And this guy should be a 0, 0, 1, 0. So here you can find that there is actually a matching between all these. Between all these vertices. So QK can be regarded as a matching between two copies of K minus 1. Okay, so on the left is a copy because we fix the starting coordinate as 0, and the remaining K minus 1 coordinates I can put whatever I want. So the left is like a copy of K minus 1, and the right is also another copy of K minus 1, and every vertex actually started from coordinate 1, and it's like a matching between two copies of K minus 1. Okay, now suppose S is any cut vertex. Let's look at this picture, and let me suppose S is any cut vertex. Let's say vertex cut. Sorry, sometimes I make this. So I should say vertex cut. So suppose S is any vertex cut, and I want to show that S has size at least k. There are two situations. So remember this picture. So maybe later I'll draw it again. So case 1. L, so this part L, this part I call R. L minus S is connected, and R minus S is also connected. So S is a vertex cut, and I suppose in case 1, the left part L minus S delete all the vertices from S, it's connected. And the same is true for the right part. R minus S is connected. So in this case, what happened? So because if you delete S, what's remaining in the left-hand side is connected, and what's remaining in the right-hand side is also connected. So all these vertices are connected. All these vertices are connected. But the whole graph is not connected because S is a cut vertex, vertex cut. Okay. So right.
I don't understand.
Okay. Yeah. So yeah, right. What I'm saying is that So what I'm saying is the following. So let me okay, good. Thank you for stopping me. So let me say this. So this structure you see, right? You understand this structure, right?
Yes.
Okay, great. So okay. So suppose S is a vertex cut, and I want to show that S has a minimal size k. That's the only thing I want to show. And I discussed several cases. The first case is that when I look at, for example, L, this is L minus S. So S is I don't know. S maybe it take some part of L, and L minus S is here, and here is L minus R. Suppose this is connected and this is connected. You see what I'm saying?
Yes.
Okay. So in this case, I'm claiming that there's no. So it's not possible. So you see. Sorry. I want to claim that there's no edge between these two parts. Let me say, there is no edge between L minus S and L minus R. Sorry, R minus S. Because if there is an edge between them, then the whole graph is connected. Then it means that S is not a vertex cut. Vertex cut will disconnect the whole graph. But it does not disconnect L, did not disconnect R. The only way as the vertex cut, it disconnects the whole graph, is that there's no edge between them. I mean, in case 1, if I assume both are connected. So both parts are connected, so they are not connected to each other. You understand now?
Yes.
Okay, so remember our structure. So it's a matching. It means that each edge, if I call it U and V, either U is deleted or V is deleted. If both U and V belong to L minus S and R minus S, then this edge is kept. So it means that each edge in this matching, each UV in this matching, either U is in S or V is in S. But there are two to the k minus 1 edge such edges. This is a very large matching. How many edges here? 2 to the k minus 1, because here you have size 2 to the k minus 1. And here, the right part, you also have size 2 to the k minus 1. And this matching has 2 to the power of k minus 1 edges. So this proves that S has size 2 to the k minus 1, which is very large. It's larger than k. So this is a first case. So in the first case, the size of S is at least k, 2 to the power of k minus 1 is very large. 1k is greater than 2. This is greater than k. 2 to the power of k minus 1 is greater or equal than k. And then, so this is only one case. And case 2, we discussed that at least one part is disconnected. Okay, so say L minus S is disconnected. So we discuss this into two different cases. The first case is that both sides are connected, and then we conclude that S is really large. And then the second case is that at least one part, L, say, it is disconnected by S. So L minus S is disconnected. But by induction here, okay, we started from induction, but we never use it. By induction, because L is a copy of Q k minus 1. So by induction, S is at least, in fact, S intersection with L, this is at least k minus 1. Okay, because here L is a copy of Q k minus 1, but S disconnected. So it means that inside here, S, the intersection of S with L has size at least k minus 1. This is a induction hypothesis. Okay? So, but we need S to have size k. So we only need one more vertex. Where to find this vertex? In another part, in part R. In part R. Okay? So what I want to say is that in part R, there is at least one vertex of S. This is enough. Okay, if not, so here, for example, this L, and you delete S, somehow it becomes disconnected. Right, this is S, for example. And suppose here, in part R, you don't have any vertex belonging to S. Then, using the matching, for example, here I have a vertex, any vertex X here, any vertex Y here. Using the matching, I can join X to X prime. And I can join Y to Y prime. And inside R, because S has no vertex in R, you always can connect some paths from X to Y. So this means that the whole graph G minus S is connected. A contradiction. Okay? So it means that S has at least one vertex in part R. So it means that because S has k minus 1 vertices in part L, and it has at least one vertex in part R. So it means S size is at least k. Okay? Okay, that's great. So it's not so simple. I think it's amazing how one example, and you have to make sure the connectivity equals k, you have to make such an argument. Okay? So I think it's a little, we are doing it very slow. So, but I think it's good we just stop here for the first part. And today I cannot, I didn't finish my plan. So what is going to happen is that later today I'll make another video. I'll record it in private and I post it on YouTube. So we stop the class for now, and maybe use some extra time you check the YouTube for the second part of today. Is that okay? because the second
Okay.
because second part of the proof is more complicated. I don't think I can finish it in half an hour. So maybe I calm down and make a video which should not be very long, but it's a theorem I want to show you. But in fact, you have enough knowledge to do the list right now. So there is a theorem that I really want to show you, but I think I will do a recording and send it to you later. Okay, so let me finish the recording for the first part.